Hello everybody, my name is Martin Dopler from METALPINE GmbH, located in the southeast of Austria in Graz. I have got the pleasure here at the virtual Formnext to talk about efficient and sustainable production of spherical metal powders. I will start with a short introduction, which you are about to hear. I will continue with the history of gas atomization, or some excerpts of that. Then I'll come to requirements on metal powders for high quality applications such as binder jetting or powder bed fusion. And then I come to sustainable powder production at METALPINE before I come to some conclusions. The company I'm representing here is part of the HDM Group, High Tech Metal Investment GmbH. It's a family-owned, Germany-based business with subsidiaries, for example, in Japan, producing aluminium powder, in Austria and France, producing magnesium alloys and magnesium powders, in Bahrain, producing aluminium alloys, and also in Graz, here METALPINE, the youngest company of the group, producing highly spherical, high-quality powders from nickel-based alloys, titanium alloys, steels or copper alloys, or also refractory metals. Now, we are doing this now for about 1 year. I'm the technical director of METALPINE. I have got about 20 years of experience in developing and optimizing metal powder production plants. I started with a master's degree in process engineering at University of Technology Graz, and then I did a PhD at University of Leoben with the topic Prediction of Particle Sizes of Gas Atomized Metal Powders. And since 2019 I'm co-founder and managing partner of METALPINE. We are located in the southeast of Graz. We have got a capacity for four production lines for high quality metal powder. Every plant will have a capacity of 100 tons per year. We are operating in a perfectly clean production environment. When I talk about metal powder production, I talk about gas atomization. You can see here a typical closed coupled nozzle or pre-filling nozzle. The melt comes through the melt delivery tube here. It comes to the edge of this nozzle face where it builds some kind of melt sheet, which is atomized here by the circumferential gas flow. Thanks to Blue Power for permitting us to show this video here. Closed coupled atomization. If you look into that with more detail, you can see the melt sheet here, which is accelerated by the high velocity gas stream. Due to this high velocity gas stream, some surface waves are built, which a little bit downstream are divided into ligaments, which further break down into these sausage-shaped fragments. These fragments are further accelerated by the gas stream. If the relative velocity between gas and fragments is high enough, those fragments tend to break down into secondary droplets. At low relative velocities, these fragments spherodize, while at the same time they cool down and solidify. If you have got a little bit of oxygen in your atomization gas, the droplets might also experience some oxidation on their surface. What is the motivation of our work? We have developed this new process to produce optimized metal powders for powder bed fusion processes, with the goal to produce perfectly spherical powders which are pore-free, satellite-free, and agglomerate-free. As we are using a crucible-free process, we expected low impurities and low oxygen content. At the same time, METALPINE committed to the 17 Sustainable Development Goals of the United Nations. So we try to reduce energy consumption and waste, and also decrease dust emissions as we are operating in the middle of a town. I will say some words about the history of atomization process development. The first document I found about gas atomization is a patent filed in the year 1886 by a person called Marriott on the atomization of liquid lead with steam. You can see here the melt pouring out from this pan and atomized by this gas stream coming out of this nozzle. About 30 years later, the US-American Hall filed some patents on the atomization of molten aluminium. You would expect here the molten aluminium, a rising pipe, and a horizontal nozzle. You can see here the circumferential gas nozzle, which also introduces some rotation in the gas stream. And due to this gas stream, the molten aluminium is aspired through the rising pipe and atomized at the nozzle tip. At the same time, Hall also filed a patent on this pre-fibering nozzle here. The melt is sucked vertically upwards, and at the edge of this nozzle, the melt is atomized by the circumferential gas stream. I think this nozzle, it's also called pre-fibering or closed-coupled nozzle, is used in about 60 or 70% of all metal atomizers in the world. Quite commonly used is also the open jet atomizer. You can see here the metal flowing through a hole downstream, and the circumferential gas stream. The metal is building an open jet, and it has got lots of possibilities to escape from the gas stream. So the drawback of the system is that the particles at the end will be coarser and have a quite wide particle size distribution. The advantage is, of course, that it's much easier to operate, as you don't have any issues with nozzle tip freezing and stuff like that. To decrease particle size and to achieve narrower particle size distributions, Hellman, for example, did the attempt to have something like an asymmetric atomization system. The first gas flow 6 here, turning the melt jet, the open jet into a film, which is atomized by the second gas stream, number 7 here, vertically downwards. Thornberg in the year 2000 even used 3 gas streams A, B and C to have a better pre-filming effect and finer particles at a narrow particle size distribution. One student of mine, Steindl, used open film, which is atomized by a gas stream from the center, and I can tell you that the particle size distribution is quite narrow, but it's quite hard to operate this nozzle. Internal mixing atomizers are commonly used, for example, for heavy fuel burners, and not so much for melt atomization, but there are also some patents and developments in this direction. You can see here for example, method filed by Baschuk 1989. The rising pipe has got some holes on top where the atomization gas is introduced and mixed with the molten metal, which rises due to the pressure that's in this tun dish. The atomization is vertically upwards. A comparable system was also filed by Wenzel, where on the top of this pressurized tun dish there is some atomization and mixing with the gas introduced into this nozzle head. High pressure gas atomization is a patent filed by Anderson and Ayers in the year 1986. It's probably the best documented nozzle in gas atomization research. Just watch out for the videos of Ira Anderson on YouTube and find his publications on Science Direct. Rotary atomization is a means to produce spherical powders with a narrow particle size distribution. You can see here the melt falling through a hole onto a rapidly spinning disk. Due to centrifugal forces, the melt forms a melt sheet on the disk, and at the edge of the disk it is divided into fine particles. They are rather spherical, but as the relative velocity between the sheet and the surrounding air is low, the particle size you would expect from this is rather coarse. There are not really fine particles usable, for example, for binder jetting or for additive manufacturing via powder bed fusion. On the right side you see plasma rotating electrode atomizer. It's a consumable electrode that's heavily rotating, and the plasma or arc is applied on the face of this electrode, melting the metal on the tip, and due to the rotating speeds, the melt is also divided into fine particles at the edge of the electrode. Also here, for some applications, a drawback that not really ultrafine particles are formed with this method. Those two atomization systems are still commonly in use. You see the electrode induction gas atomization system on the left. It's a rotating electrode, for example, made from high melting point materials or from high purity. For high purity applications, as there is no tundish, the number of impurities in the product is decreased. It's rotating, and at the same time it's molten from this electrode, from this induction coil here. On the other hand, it's a free fall atomizer. The melt is flowing down through this nozzle, and atomized particle sizes are not really fine, and particle size distribution is rather wide. On the right hand side you see plasma atomization. A wire is introduced into this atomization tower, and 3 plasma guns shoot at the wire and produce quite spherical powders. This leads me to the requirements on metal powders for high-tech applications such as powder bed fusion. With a little bit of imagination, you can see here a powder bed and a laser running around to produce these complicated, highly functional parts that you can produce with powder bed fusion. And as the size of the laser is not really much bigger than the biggest particles of the powder bed, you would expect that any bad particle, any agglomerate or any other mistake here in the powder bed might probably lead to defects in the printed part. So requirements on the metal powders are above all a good flowability, a good predictability of the process, and a really low specific surface area to decrease the number of impurities and oxides. So you can have less evaporation and less defects in the printed parts, and better powder quality also leads to a higher printing speed in the end. So, of course, spherical particles are flowing better and have got a lower surface area than the particles which result from a grinding process here on the right. But you would also want to have only very few agglomerates, as any agglomerate leads to, may increase the probability of defects in the printed parts. And you see also a lot of satellites in this picture here. Imagine these small particles. When the laser goes over this small particle, it will immediately evaporate and also increase the probability of defects in the printed. At the end, you will also want to have pore-free powder. Above all, for pre-filming atomizers, a lot of pores or hollow spheres in the powder appear as there is really this thin melt sheet on the nozzle tip. The METALPINE process produces rather pore-free powder. You can see it here on the right. Any pore in the powder will have some gas in it, and when the laser heats and melts the powder particle, the gas in the pore may make puff and also increase the probability of defects in the printed part. So, to conclude, spherical particles, no agglomerates, no satellites, pore-free powder. That's what you want to achieve, to have a good flowability, a good predictability of the whole process, and at the end, less defects in the printed parts and a higher printing speed for your economic production. I now continue with sustainable powder production at in Graz. We committed to the Sustainable Development Goals of the United Nations. In the first line, to decrease energy consumption and to decrease dust emissions. We also want to decrease waste, which also means we increase the product yield. And the main energy consumer in metal powder production is the inert gas consumption. So the decrease of inert gas consumption is also one of our main focuses. Our in-house developed atomization system has got a really small physical footprint of less than 25% of that of standard atomization plants. Nevertheless, we have got a capacity of 100 tons a year for any of our atomizers. We have got a dust emission-free process in Graz. We have got a clean production environment for highest product quality and, of course, environmental and personal safety. We have got a really high product lead for powder bed fusion, for example, more than 70% for copper or nickel-based alloys or stainless steels in the range of 15 to 45 microns. With our in-house developed atomization system, we achieved a high reduction of energy consumption. You can see here the main contributors on energy consumption. The first one is the melting of the metal. Then we have got the superheat of the metal. If you want to, also the gas heating plays a role. But the main energy consumer is the gas supply, the inert gas supply. And with our in-house gas recovery system, we can reduce the energy consumption by more than 70%. So I finally come to some conclusions. The motivation of our process was the production of optimized metal powders for powder bed fusion processes. I think I could show you that we can produce spherical powders which are pore-free, satellite-free and almost agglomerate-free. And we also can reduce the energy consumption and the waste production, as we are committed to the 17 sustainable goals of the United Nations. If you need powders, for example, from copper alloys, from titanium alloys, from nickel-based alloys, or also from stainless steels or tool steels, don't hesitate to contact us. Also, if you want to have refractory metals, we are the company to talk to. Thank you very much for listening.